we need to stay on schedule. And with that, I would like to move forward and introduce our very first speaker, Dr. Burt Davis. He's leading off the symposium, and he's from the University of California, Davis. This is a collaboration with Oak Ridge National Lab, and Professor Gates has received so many awards that it is almost impossible to list them all here, but I would like to just note that he is the North American Catalysis Society Robert Berber Lecturer recipient, and he's a member of the Society of the Boards at NACS. And obviously, in just 2 months, we will have the NACS meeting in Louisville, Kentucky, and we hope you can join us there as well. We would like to just now invite Dr. Gates. Thank you very much.
Thanks, Ushi. Thanks for the invitation, and especially an honor and privilege for me to be here honoring Burt, whom I've known for more years than probably he wants me to say. And I've had so many nice discussions with him over the years about reforming and supported metals and acid catalysis and Fischer-Tropsch catalysis, and maybe even more interesting than all those, history of catalysis. If you don't know him, you should get a chance to talk with Burt sometimes about history. He has lots of interesting stories, even salacious ones, that he will share with some friends. But he's certainly got a sense for history that, in my mind, is unmatched among people I've ever met. And it's lots of fun to hear from him about the history. Well, this is historic, to honor Burt as historic. And my privilege to talk about one of the subjects he's been interested in for quite a long time, supported metals. So we're interested in understanding the most highly dispersed supported metals, trying to understand them fundamentally. And what I'll talk about now is how we can understand them structurally. So our focus is on osmium, and I'll explain why in a minute. It's because we can understand it well. Osmium is the metal and magnesium oxide is the support. And we're choosing both of those so we can understand, well, fundamentally what we have. So our goal is to start to make supported catalysts that are structurally simple and well-defined, and then to move from the simplest towards more complex. And you can see we get to substantial complexity, but far, of course, from the goal of understanding supported metals that are typical industrial catalysts. So the technique I'm going to talk about the most, the one that's helped us the most, is scanning transmission electron microscopy, aberration-corrected microscopy. This is a field that's really revolutionizing the investigation of catalysts, I think. We're now able to see metal atoms, heavy metal atoms on supports, and that's kind of the gist of the story that I'm working on. So I'll mention spectroscopy along the way. It's important, but I don't have time to say a lot about it. So what we're investigating is a very heavy metal, osmium, on a support that consists of light atoms, Mg and O. And that choice gives us a chance to do investigations at the atomic scale of the metal. And so the keys to doing this well are the preciseness of the synthesis, that's to get us started in this field. And then there are a lot of caveats about microscopy that I don't have time to talk about very much, but will pop into the story. So we're working in, at least in this vein, with osmium, iridium, platinum, gold, all heavy metals, heavy enough to image, on supports that are very light in terms of atomic weight of the constituents. So I'm going to talk about MgO at this event, but we've also been doing a lot with zeolites, and just don't have time for that part of the story. And the advantage of MgO is that it's crystalline, so in the high area powder form, what you're looking at in the microscope is faces of little crystallines. So it's a poor person's surface science, really. And we can look at various faces of MgO, and that helps us to understand what's on the MgO, and it's going to be osmium in this story. And so the other advantage of osmium in all of this is that we can do synthesis in a precise way based on organometallic chemistry. So here's the parent compound that we start with, OS3CO12. You can buy this. It's got a very rich chemistry, very rich literature that goes back decades. And the important thing for us is it's got a stable framework, as does this one, which is an Osmium 10. So this is the biggest one we're going to talk about. And so in these frameworks, I'm emphasizing the metal atoms, and I also have to emphasize the ligands that are stabilizing the metal clusters are carbonyls. So we're building from the foundation of osmium carbonyl chemistry, so molecular chemistry, solution molecular chemistry, with a whole family of compounds that are characterized well, meaning categorized in terms of their crystal structures as well as reactivities. So the reactivities we're taking advantage of are those that take place in basic solutions, which we can translate onto the basic surface of MgO. So there's another advantage of MgO, is that it's basic. And so I'll just give you a thumbnail sketch of some of those reactions. So if we start with our parent compound, the triosmium carbonyl, with its triangular metal frame, we can oxidatively fragment it. So if it's adsorbed or something that forms from it, which we'll talk about in a minute, if it's adsorbed on MgO and treated even under these conditions, fairly mild conditions, which are oxidative conditions. You do the same thing by exposing it to air, but it's the hydroxyl groups on the MgO that are the oxidizing agents that oxidatively fragment the cluster carbonyl to give a mononuclear, that is a single metal atom, osmium carbonyl. So if you keep this in mind, this is a single metal atom with a couple of carbonyl ligands bonded to it. And there's lots of work in our literature with rhodium analogs and iridium analogs and so forth of this. Now, with this as a starting point, one can make larger clusters. So one can make the 4-atom cluster, and this is an anion. On the basic support, we get anionic structures. 4-atom cluster, we can go this way. I'm not showing all this. This is chemistry that's been worked out to get pretty high yields of these different species, but it's more complex than this. One can get a 5-atom cluster. One can get the 10-atom cluster. There's a 6-atom cluster that's reported, but not yet reported on surfaces. So we can, by virtue of controlling the conditions, reactions that involve oxidative fragmentation, and really the reverse, reductive carbonylation, treat samples to get clusters of various sizes. So we're going to do more or less one at a time of these, and then we're working towards characterization of mixtures. So I just want to remind you the structures of the metal frames, because this is what we can get at with the microscopy. So here's the parent, the triangle, Os3, Os4, Os5. There's a carbidocarbon helping to stabilize that framework in the metal carbonyl. And here's the Os10, and there's a carbidocarbon there, identified by carbon-13 NMR spectroscopy, that helps stabilize that frame as well. So I'm going to emphasize characterization by the microscopy, and I don't have time to talk much about the others, but a bit will come in. The carbonyls give a lot of information in the infrared spectrum. XAFS is crucial for all of this to get structural information that complements the microscopy, or probably I should say vice versa. And Zanes, turns out, we're learning that Zanes is especially important to track conversions of one species to another. And when there are isospecific points, then we see we have a stoichiometrically simple conversion. Sometimes we do. And when we don't have those isospecific points, then it's more complex stoichiometrically, which is typical. So we get a lot of information relatively straightforwardly just by looking at the Zanes, even if it doesn't provide too much structural insight. Okay, so let's go back. You can't see the bottom, it's cut off a little bit. But a few years ago, we did some conventional high-resolution electron microscopy, scanning transmission electron microscopy, characterized what we made by absorbing the triosmium clusters on MgO. And I'll come to the details of that, but the cluster frame remains intact. And the evidence for that is, we look at the images, and this is not impressive by today's standards, but it's analyzable, and maybe with this light you can't see too much, but there are clusters discernible there. And with a lot of data analysis, that I don't have time to go into, but it's involving smoothing and statistics, one can determine the average diameter of the supported clusters from the microscopy. There's that diameter. And if one determines spectroscopically what the predominant surface species are, and the infrared and the XFs lead to that, then you get triosmium carbonyl, and it's lost at one CO ligand and it becomes an anion. So it's still triosmium. So one can, using crystallographic data for that parent compound, calculate the dimensions of the clusters from the XFs, and the values match. The XFs and the microscopy values match, which says that we've done the preparation effectively, that we've gotten a high yield of the desired triosmium on the support, so which is reassuring. It means if we're trying to make simple samples, we succeed. So now let's go to the same sample, but characterize it with better quality microscopy. So this is aberration-corrected STEM. And what you see on the left now is that we have resolution. I hope you can see it in the back. We can see the three atoms in the three atom clusters nicely resolved, and we can determine the osmium-osmium distance, the average distance, which is this. And then by XF spectroscopy, obviously from the osmium-osmium contribution in the XFs, we can determine the average osmium-osmium distance. And within the error, those two are agreeing. So that's a further reassurance, and it's also a demonstration of how much detailed information about supported metals one can determine with this microscopy today. So remember that the triangle of osmiums and triosmiums is planar. Now, whether each of those is planar, of course, depends on the orientation of the sample and what face of MgO and the microscopy. But it's especially advantageous, and of course we're showing some of the best images, to determine a structure of something that's flat, okay, so a triangle. So we're going to go to the more complex ones, but I should put in the caveat that this experimentation isn't so easy because the electron beam affects the samples. So within a minute or so, you see that we have different structures on the surface. So this is part of this challenge, is to get the samples into the microscope without any air contamination, and to get the images quickly and deftly. It takes a very good experimentalist to do this before the structure changes under the influence of the electron beam. Okay, so let's now start marching through a set of samples formed from the parent triosmium. So we're going to make isolated osmium atoms on the MgO from the triosmium. So this is the oxidative fragmentation reaction. So we do the adsorption, we get the triangle with one fewer carbonyls. I'm not showing you the spectra, but they bear this out. And then this oxidative treatment leads to the fragmentation, and there's some spectra I'll show you a few later, but not now, and whereby we break the triangle into individual osmiums. So here are the triangles, and here, for example, are the isolated single metal atoms. So we're doing the oxidative fragmentation. We can characterize that well. So here are a few spectra. So if we start with the triosmium and we go to the mononuclear osmium and look at the zanes, we see the isospestic points that say we're doing that conversion in a stoichiometrically simple way. So it's a sharp synthesis. And we do infrared, and it bolsters what I'm saying, so we get osmium dicarbonyls. So we have a simple sample to work with, and we can push the microscopy to learn something important about the structure, not just of the metal species, but of the metal support interface. So we think that's an important part of what the microscopy is bringing to catalyst characterization these days. So if you want, it's the simplest kind of sample. It's a single little metal atom kind of catalytic site. Lots of stuff going on in this field with platinum, with gold, with a number of things these days that are drawing researchers into the field of isolated metal atoms, usually cations, of course, on surfaces as catalysts. Some of them are quite stable. And if you look at Beretta, Flizzani, Stephanopoulos' recent work, you get an idea how rich this field is. So what's important in this is that if we look at the osmium on one particular face, it's this, where did I write it? It's the 110 face of MgO. That's especially, we're going to keep coming back to that face, especially good for structure determination. And what we find is that the osmium atoms, I don't think you can see it well enough from this image, but the osmium atoms are atop magnesium atoms, or columns of magnesium atoms. So if you're looking onto this face of MgO, then you're looking down. If you take a top view, you're looking down on columns of Mgs and columns of Os. And so it maximizes the contrast, and it turns out that the osmium atoms are directly above columns of magnesium atoms. So that gives us a basis for determining a structural model. And the key that we need to get beyond just the microscopy is the XAFS evidence. And so we're getting, so let's go to the mononuclear when we get an osmium-oxygen coordination number over the whole sample, various faces of MgO, it's 3 or 3.5. And so what we're inferring on this particular surface is that the value must be about 4. This is, of course, a model. And so we've got the distance, and it's the bonding distance, just what one expects from lots of similar samples. And so one can build a model with that osmium-oxygen XAFS distance. Remember, it's an average over the whole sample, all the faces, not just the face we're looking at, so it's an assumption, but it's chemistry. And then we can put 2 carbonyl ligands in, and so we can determine a structural model, and I'm not going to show you all the details, but there it is quantitatively. And the important point about this is that if the osmium is bonded to 4 oxygens, and it's certainly bonded to approximately 4 oxygens, then the osmium-magnesium distance has to be greater than what it would be if the surface were ideal and intact. So the inference is that there's a defect site, there's a missing magnesium there to accommodate the osmium carbonyl. So there's a lot of detail coming out about the interface structure following from the microscopy with some bolstering by the spectroscopy. Now let's go back to the triosmium because we can learn about the interface structure here as well. So I'll show you a few XAFs. So osmium-osmium coordination number is about 2, as you expect for a triangle, so the triosmium is intact. And even with this as a metal carbonyl, all these are metal carbonyls, the osmium-oxygen distance here, about what I showed before, with an error I would say the same, close to the same. This is a bonding distance, even though we still have carbonyls. To interpret that, one has to assume that there's some distortion of the ligand sphere around the osmium so that the osmiums get close enough to the oxygens of the support to undergo bonding to that support. So we can do the microscopy, as I showed you. We can do the spectroscopy, as I'm showing you, and infrared as well. We can get the distance, compare the distance, find good agreement, and then we can go to a structural model that takes again account of the observation from the microscopy, and this is what we didn't anticipate, that even with the triosmium on this 110 surface of MgO, the osmium atoms are atop the columns of magnesium atoms. And so that gives us the key to do structural models. So the structural models, the student did all the geometry. Thank goodness the student did it and I didn't. Figured with this face of MgO, with it hydroxylated or non-hydroxylated, placing it with the osmium-osmium distance matching the experimental value, and the triangles you saw were isosceles, so they're not planar, they're not perpendicular to the beam. So it becomes a geometry problem, but one can figure out that the only way the osmiums are atop the magnesiums if the clusters are tilted with respect to the plane perpendicular to the beam, and the tilt angle turns out to be 38 degrees. And so what one is doing here is simply using the results of the microscopy in constraining the osmium-oxygen distance, there you see it in this model, to be in the range of that determined by the X-ray spectroscopy for the average samples. Okay, let's go to now slightly larger clusters. I'm watching the clock. There's two nervous people sitting next to me. So we can start with the triosmium on MgO, and we can treat to fragment, and then we can treat in CO at higher temperature. And the temperatures are going up here to reductively carbonylate to make larger clusters. So we can go from the triangular frame to the deca-osmium frame. And so I'll be brief about that, but we've used the microscopy to characterize what are predominantly the deca-osmium clusters. We did the synthesis to try to get as high a yield. You can get 65% or so yield of the deca-osmium on the support. And we do the microscopy and then obviously do the spectroscopy and get comparable values for the size, this radius 2 times that diameter of the cluster. So again, satisfying agreement between what this time is conventional microscopy, conventional STEM, not aberration-corrected STEM, and the spectroscopy. So we've made these in pretty high yield. Okay, so now the next step is to try to say, all right, suppose you've got a mixture of these clusters. What can you learn by microscopy and spectroscopy to try to resolve the mixture? So we're taking a step towards the complexity of industrial catalysts, but it's maybe you would say a small step, because the clusters are still going to be small, and the complexity in terms of structure is not going to match that of a maybe typical industrial catalyst. So what we've done is we've taken a sample, made it from the triosmium cluster, treated in helium to fragment the clusters, as I mentioned before, then treated in CO to start forming larger clusters, and we chose the conditions to get a mixture. So not just OS10 or OS5, but a mixture. And then looked at that sample in the aberration-corrected STEM and analyzed a whole bunch of samples. So the student, Sharon, I did lots of research analyzing these samples. And what I have to tell you at the outset is that we're not able to analyze every image of every cluster, at least in part because the orientation's not optimized, and it's only the ones that we could elucidate the structures of that I'm going to show you. So I can't tell you these are the only species on the surface, but they're certainly not little minority species. They're major species on the surface, but there's more to do to understand the details of what's on the surface. So what do we see? Well, what we see is what we've seen. So here are triangular species. So I'm putting the framework structures in that kind of blue-gray. So here's the triosmium, and here are a number of images in which we see triosmium, and I don't think one would dispute that those are really triosmium. And then beyond that, tetra. So here, 4-atom cluster, here, 4-atom cluster, and so forth. So now we're really resolving 3 from 4-atom clusters. Then 5. So count them, 5. So you might start disputing what I'm showing here, so I'll come to that in a minute. And then all these, category D, are the deca-osmiums, the osmium 10 clusters that I showed the structure of near the beginning of the talk. And so you might be a little more skeptical of what I'm showing you. That's your privilege. So maybe a little more specific about how we're determining the number of metal atoms in each of these clusters. So what we do is an intensity analysis, and I'm not going to give you detail about this, but my students spent months doing this. So take one particular image, like this one, which we call a deca-osmium, do the intensity analysis, and see, count them, 10 osmiums indicating that it's really a deca-osmium cluster. And then she did statistics on all of this, and again, I won't go into the detail. She subtracts off the effect of the MgO support, which is variable from place to place, uses isolated osmiums, which remain in the gemisch after this synthesis as a kind of standard, and then does the intensity analysis on the basis of that as a reference, as a standard. And so consistently finding evidence of the number of atoms that I'm inserting in each of the clusters. And you know, one of these you see a smear, and what that's telling you is that we're kind of at the edge because there's been motion of one of those osmiums, substantial motion, under the influence of the electron beam. So we're at the edge in terms of what we can resolve structurally with the microscopy. So I want to summarize what we're doing here is by using aberration-corrected STEM, we're now able to fish out, we can make in high yields and fish out species with nuclearities going from 1 to 10 because of the opportunities afforded by the chemistry of osmium carbonyls. We can determine cluster sizes and metal-metal distances. Matching those, we determine spectroscopically, which is evidence that the syntheses have been done precisely. And then we can resolve mixtures. And I guess the point I should emphasize with this is that they're 2D images used to infer 3D structures. So there's clearly an inference there. And also the assumption, which seems to be consistent with all the data, that the metal frames have structures that match those of the parent compounds. Pure compounds with known crystal structures, which are osmium carbonyls, like the OS10C CO24 2-. So that's, you might say, fortuitous, or we might say we chose a good research direction to get into this field. And so the bottom line importance about this is not only can we get quantitative structural information about the supported metal species, we can get information that's also quantitative about the metal support interface structure, and that requires using spectroscopy in combination with microscopy. So I want to say thanks to a bunch of people who did this work. The microscopist, well, Nigel Browning's my colleague, who's a superb microscopist. I appreciate this collaboration very well. And the student who did almost all of the imaging was Sharon Iden, and Apurva Kulkarni did a number of those images as well. I want to thank the organizers again and thank Burt again for all he's done for the catalysis field. It's very nice to be part of this. Thank you.
Thank you very much. We have time for one or two quick questions. Yes, go ahead.
Well, I just want to say, anytime that you can get XFs and high resolution TEM to match up, you're doing pretty well.
Well, yeah, the matching of the XFs and the microscopy is evidence that the synthesis was straightforward. And that's where what we're doing is a little unconventional, and we're doing not preparation in typical ways, but we're trying to make the samples simple.
Thank you very much. A very nice talk. I was a little late when I came in. Have you done some work with ruthenium or the rhodium carbonyls? Because I chose osmium because they're...
Yeah, so the questions, have we done with ruthenium or which other one's rhodium?
Yeah.
Rhodium and ruthenium. The answer is yes. The microscopy is more challenging because they're lighter atoms. And so we've relied much more on the spectroscopy and less on the microscopy with those. But in fact, you've asked a question that's kind of motivating a lot of our current research, because we're studying bimetallics, and we're studying the formation of bimetallics using osmium kind of as an anchor point, and combining with rhodium, combining with ruthenium, and taking advantage of the ability to, again, build on the metal carbonyl chemistry to understand what's going on. We've got a lot of levers to pull about the control of bimetallic formation because of the different reactivities of the different, essentially, organometallics that we can put on the surface. It's, I think, a very rich field.
Thank you.
If there are no more questions, thank you very much.
Thank you. you.